Okay, so we're starting chapter 9 today. Chapter 9 is the general topic for the chapter is differential equations. Inside of this chapter, we will be studying the concepts of exponential growth and decay, which will really be mostly in the context of population growth and decay. We will learn how to solve a differential equation, which is a big deal on the AP exam. We will learn slope fields, which is basically it's a way to get a visual representation of the solutions to a differential equation. It's kind of funky, but it's fun. Like most people like slope fields. So we'll learn slope fields. We will learn Euler's method, which is a way of approximating the solution to a differential equation. And we will learn logistic differential equations and their solutions. And then we'll be done. Yes?
Why is there a picture of a cheetah chasing?
Such a good question. I think it's a warthog. Yes. So, like the Lion King. I don't know the warthog's name. Timon? Pumbaa? Okay. All right. So, anyway, yeah, I don't know. Maybe to represent, because we're doing population growth and decay, it's, life.
And death.
And death. Yes. No motion. No motion problems. Nope. But I think it's about like circle of life kind of a thing. Is what they're representing. No, there's no circles.
No, I think Matt just put random pictures in there.
That could be too. Just searching the internet and saying, "Hey, look at this one. Let's stick this on a slide." So, okay. All right. So today is modeling. So today is they're kind of starting you with applications of differential equations, just so that you kind of get a general idea of how differential equations can be used. We are going to focus on one particular model, and then I'm just going to show you a couple others just so you know they're there, and then we're going to switch and start working through your homework. So today we're doing 9-1. I can model with differential equations. So you're going to learn about them. You're not supposed to learn how to solve them today, but we are going to solve one just so that you kind of see how this works. All right. So first slide, no writing. Just chillax for a minute. All right. The mathematical model often takes on the form of a differential equation. A differential equation is just an equation with a differential in it, right? A differential is dy, dx, dt, right? D anything, right? Those are called differentials. Differentials, remember, represent the limit as delta y or delta x or delta t, the limit as that approaches 0, right? So it's a teeny tiny value that represents instantaneous change in whatever it's talking about. All right. So the mathematical model often takes on the form of a differential equation, which is essentially an equation that contains derivatives. This is not surprising because in a real-world problem, we often notice that changes occur, and we want to predict future behavior on the basis of how current values change. Remember that a derivative gives you an instantaneous rate of change. So if you have a derivative in an equation, it's talking about a rate of change and how that rate of change relates to other stuff. Let's begin by examining several examples of how differential equations arise when we model physical phenomena. So, one model for the growth of a population is based on the assumption that the population grows at a rate proportional to the size of the population. So this is like the original model for standard population growth. And what this means is whenever you have an environment with no limiting factors. So say you have just this perfect environment. I like to, human population, there's limiting factors all over the place. But say you have a controlled environment and you have this lovely petri dish and you put, a couple bacteria in there and then you just let them go, right? And right? Until they hit the size of the petri dish, there's no limiting factors. It's just growth, right? So when you have that just perfect exponential growth, it follows a model that is based on the fact that the rate of change of the population, meaning the rate of growth of that population, is proportional to the amount that's there at any moment in time. So at any moment in time, if you're studying the rate that it's growing, it's proportional to the amount that's there. So because of that, the rate of growth is called dp/dt, the rate of change in population over change in time. So P is population, T is time. So your standard differential equation for population growth is this guy right here, dp/dt equals Kp. Now K is called the constant of proportionality. It represents a constant. It's a multiplier. That's all it is. It's a scalar multiplier. So what you're saying is the rate of change of the population is some scalar multiple of the actual population at any given time. So K just represents a constant. This is called a first order differential equation because it has a first derivative in it. If you have a second order differential equation, that means it has a second derivative in it, right? Third order would have a third derivative in it. Okay, so and so forth. Most of the differential equations we will deal with will be first order differential equations. All right, so what we are going to do is we're going to solve this. This is not a part of your book's plan for this section, but I want to do it as kind of just an introduction on solving differential equations. So if you haven't written this somewhere, write this on your paper. Now this type of differential equation is called a separable differential equation. A separable differential equation is an equation where you can separate the variables. Now, if you look at this, there's a lot of letters here, right? There's no numbers at all. It's just all letters. But there are only two variables. What are the two variables? P and T. Because D is your differential operator, and K is a constant, right? Not a variable. It represents a constant. So your only variables in this whole equation are P and T. So when we talk about a separable differential equation, there are non-separable differential equations, but we would not do them in this class or next year. You would learn them in a class called differential equations, right? If you want to go up higher in math. So anyway, but everything here is going to be separable. So what we want to do is we want to get the P's on one side and the T's on the other side. Separate the variables. P's go here, T's go here. How do you know which side to put them on? Your differentials, the dp and the dt, have to be up in the numerator. You can't divide by your differential. You don't want like p over dp. You have to be times your differential. So whatever puts the differentials both on top, that tells you which sides things have to go on. So since the dp is on top on the left, that means the p's have to go to the left and the t's have to go to the right. So the first thing we're going to do, I'm going to write out steps here, is we're going to separate the variables. So the way we separate the variable is we're going to, what am I going to have to do to move this p? What am I going to get on the left? I'm going to have to divide. So I have a 1 over p dp. All right, now all my p's are on the left, and then I got to multiply by dt to move it to the right. So multiply both sides by dt, and you get k dt. Does the k matter? No. Always put if there's an unknown constant, put it with your input variable. Don't put it with your output variable. Put it with your input. So keep the k with the t's. All right, everyone okay with understanding how we separated them? Not so bad, right? Okay, so the next thing we're going to do, so we have this equation. How on earth do we solve this? we're going to integrate both sides. So we're going to have the integral of 1 over p dp equals the integral of k dt. So we have to integrate 1 over p dp. What function has a derivative of 1 over p? ln absolute p. So I am not going to write ln absolute p. I'm going to be a rebel and just write ln p. Why am I just writing ln p? Because p represents population. So if p represents population, you can't have a negative population, right? Without zombies. So because of that, since we are assuming population is always a positive number or 0, we don't need the absolute value, so you can just ignore it. If you don't have any context, then you have to put the absolute value. Yes? And when you do an antiderivative, that goes away. Right? Okay. What's the antiderivative of k dt? Kt, because k is a constant, right? It's not 1/2 k squared. K is not a variable. K is a constant. So this would be kt, and then what am I missing? Plus c. Is it okay that I just write 1 plus c for the whole equation? Yes, because I can take all the unknown constants, all the constants on both sides, and just lump them all onto one side. So always lump them onto the side, again, with your independent variable. You always want to put as much on the independent variable side as possible, because the next step is you're going to have to solve for p. So always, when you can, put stuff on the other, away from your dependent variable. All right, so the next thing we have to do is solve for p. All right. Oh, and I'm going to put a little note here. Let's see. It's not going to start with whatever letter that was. Okay. No absolute value because p is population. Okay. All right. So I got to solve for p. Oh, just so you know, guys, I put an extra tissue box over there, like by the, see the washcloths, like by the, yeah. So if anyone else needs to, you're welcome to come over here, but there's some on both sides. Okay. So now we got to solve for p. So what am I going to do? How do I get rid of that ln? Yes, that's called exponentiating. I'm going to exponentiate both sides, right? So I'm going to make each one a power of e. I'm going to write it out. I know you all know that the e and the ln are going to go away, but we're going to go ahead and write out all the steps just so you can see it. So I have e to the ln of p equals e to the kt plus c, the whole side. You don't get to pick and choose. It's not e to the kt plus e to the c. That's not how math works, right? It's like if you square both sides, you have to square the whole side, right? Not each part. So e to the ln of p, that's just p. So we have p equals e to the kt plus c. Now technically, this is solved for p, but we're going to do one more thing to clean it up a little bit more. So I'm going to do something algebraically, and I want you to take 10 seconds and see if you agree. Yes. Because you disagree? Because when you are multiplying with exponents, you add the exponents, right? Does that make sense? Okay. All right, so we can go do it backwards. We can break it up. So E, what is E? Is E a variable?
No.
E is a constant, right? Around 2.7? All right, what is C? C is a constant. E is a constant. C is a constant. So E to the C is a constant. So I'm going to call E to the C another constant. Now I can't call it C because I've already used C, so I'm just going to call it A. You can pick whatever letter you like. So we used to have students who would call it M so that you had me, right? But, okay, yes.
But is it, T is not a constant.
No, T is not a constant. but I'm not replacing the t. The only part I just changed was this guy right here. I'm just giving it a new constant name called a.
Oh.
This part
yeah.
I kept.
Got it.
I just moved it to the front. So it's a coefficient. All right. Does this look familiar? What does it look like? It's there. What's that formula? Yeah. With letters. What is it? PERT. It's the PERT formula, right? PE to the RT? Yeah? Do you guys remember PERT? Standard exponential growth? Continuous? You did it in algebra 2. I'm sure you did it again in pre-calc. You don't remember PERT?
No.
I didn't call it.
So anyway, if at some point in your life you ever learned A equals PE to the RT, right? This is that, just with different letters, but it's the exact same formula. What you did was you just derived PERT. So whenever you are using PERT, which now we're going to call probably CE to the KT, because that's what most calculus students do. Whenever we use CE to the KT, which is the same as PE to the RT, just know that this is a model for population growth based on a population that grows with no limiting factors, which means that the rate of change of the population is proportional to the size of the population at any given time. You base it on that model, you get PERT. All right, moving on. So what they're showing here is if we were to graph those solutions, right, A, E to the KT, so you with different values of A, they're calling it CE to the KT, so with different values of C. Well, this is population. It says population equals this, right? We can't have a negative population, and E to any power is positive, which means C has to be positive. So because C has to be positive, we can just get rid of all of those answers. And technically, most of us think of time as being positive. So if we control like time and say you can't have negative time, which, you know, in some circumstances you can, but anyway, you can't have negative time, can't have a negative population, then this would be a set of graphs of the solution to that differential equation. Obviously, it's not all of them. If it was all of them, it'd just be a big solid block of, you know, of lines, right? But it's just like, hey, what if, you know, let's say we graph it where C is 1, 2, 3, and 4, right? Something like that. Then you get these different exponential growth graphs. All right, so this would be called, they call it the family of solutions. So this would be kind of like a family of solutions to the differential equation. Okay, so that's the first type. However, one more little thing about it. At t equals 0, if you were to plug into C to the KT, if you plug a 0 in, what does e to the 0 equal? 1. So at time 0, your population is equal to C, which means C is your initial population, right? We kind of talked about this on that weird day with section 3.8 or something like that, when we did that extra section. I don't know if you guys remember that. But anyway, so this number is your initial population, whatever it happens to be. All right, under this model. However, later on, scientists realized that a more realistic model was necessary because most populations don't just grow forever unchecked. Most populations have limiting factors such as geographical limiting factors. There could be, you know, access to food. There could be illnesses, right? Whatever causes populations to reduce. So there are different factors out there that curb the growth of populations. And because of that, a new model was created. So this new model looks like this. dp dt equals kp times 1 minus p over m. So this 1 minus p over m, m represents like the highest possible population that could be supported based on the resources available. It's, m is called the carrying capacity. So I will tell you, College Board always calls it L. I don't know. Your book calls it, I guess different people call it different things. So anyway, but this is representing your carrying capacity. So if your population is getting close to the carrying capacity, then the rate of change is approaching 0, because you end up with basically m over m, which is 1, minus 1, which is 0. So you end up with a rate of change of 0 because you can't grow anymore because you're hitting that carrying capacity. All right, this first order differential equation is called the logistic differential equation and was proposed by the Dutch mathematical biologist Pierre-Francois Welhurst in the 1840s as a model for world population growth. We first observed that the constant functions where p equals 0 and p equals m are solutions because in either case, one of the factors on the right side of the equation is 0. So if your population is 0, then there's no growth. Okay? If your population is m, there's no growth. Okay. All right. These two constant solutions are called the equilibrium solutions. No growth, no growth or decay just means like your population is stagnant. It's not growing, it's not decaying, it's just staying the same, right? Equilibrium solutions. All right, and then this is just kind of a graph of what that looks like. Logistic models tend to, like when you start off, you kind of start flat, and then you grow, and then you start to flatten out again as you hit that carrying capacity. So that's more of a logistic model. All right, one more example, which you don't have to know, but they're just trying to show you of a possible model using a second-order differential equation. So one example of a model that uses a second-order differential equation is when you hang a mass from a spring, right? Because we love hanging masses from springs. Those of you who've had physics, right? How many of you had physics and had to hang a mass from a spring? Okay, all right. So anyway, or push an object up an inclined plane, right? Those are the two things I remember from physics. We're always pushing boxes up inclined planes, and we're hanging masses from springs. Okay. So anyway, all right. So when you hang a mass from a spring, there is this thing called Hooke's law, which says that if the spring is stretched or compressed x units from its natural length, it exerts a force proportional to x. So your restoring force equals negative kx. So k is some positive constant called the spring constant, ignoring any air resistance or friction. By Newton's second law, which is force equals mass times acceleration, then what they've done here is they're saying acceleration, which we know is second derivative, right? So times mass, so force equals mass times acceleration, divide by the mass, you got acceleration equals negative k over m times x, because the mass would be constant, right? So anyway, so second order differential equation that can be solved. We're not going to guess about the form of the solution right now. I'm going to show you, because the next slide is just problems to get you ready to help you do your homework. But instead of doing the problems to get you ready to help you do your homework, we're going to do your homework, right? Okay. All right. So like that's, yeah, this is just showing you how to solve. So we're going to skip these. All right. Do you think I should record while we walk through this too? Yes. Okay. Okay.
Yeah, before Keegan, he's gonna have to do all this work by himself.
Yeah, but then he'll just be able to follow the video and piece of cake, right, Keegan? You got this. Here we go. This is for you.
Why are you looking at me?
Other Keegan or Faith, right? Both of them. Okay.
So are you recording right now?
What I am. Okay. What can you say about the graphical solution of the equation y prime equals xy cubed over 16 when x is close to 0? So now yours might be over a different number, but the answers are going to be the same. So what can you say about the graph of y prime equals xy cubed over 16 if x gets close to 0? What does this get close to when x gets close to 0? 0, right? What about when x gets really big? What happens to this? It gets big, right? Okay, so if x gets close to 0, then xy cubed over number is close to 0. And hence, y prime is close to 0. Thus, the graph of y must have a tangent line that is nearly horizontal, because slope is approaching 0.
Wait, how is it horizontal?
Because this is y prime.
Yeah.
If y prime is approaching 0, that means your slope is approaching 0, right? Which means your tangent line would be horizontal. Okay. All right. If x is really big, if x is large, then xy cubed over number is large. And the graph of y must have a tangent that is nearly vertical. Okay. In both cases, we assume reasonable values for y. Now, here's where we get into some of the math. So I'm going to show you how this works. Verify that all members of the family y equals 4 times c minus x squared to the negative 1/2 are solutions to this differential equation. They don't want you to separate and solve this. What they want you to do instead is plug this into here and see if it's true. So we have to plug y in for y, and we have to find y prime and plug that in for y prime and see if what we get is true. So the first thing you guys are going to have to do is you're going to have to find the derivative of that guy. So go ahead and take a second and find y prime. Might have to actually use some paper. I don't have access without minimizing to pause the recording, so we're just going to let it go. Don't forget chain rule. Right, yeah. Do you remember how to do this? It's been a while. Okay. You're going to walk me through it. Are you ready?
Yeah.
Okay. Remember when you do a derivative? So what's negative 1/2 times square? Negative 2 times c minus x squared to the... Remember you subtract when you're doing a derivative, right? And then chain rule says we have to multiply by the derivative of the guts. C is a constant. Negative 2x. Yeah. It's hard when we've been doing so many integrals to switch to derivatives. All right, everyone good? So if we clean this up, I get, now you might have different numbers, I get 4x times c minus x squared to the negative 3/2. Now if you look at what they want you to enter for y prime, they have y prime equals box times c minus x squared to the negative 3/2. So in this one, like on mine, I would put 4x. That says 4x, sorry for that handwriting. Because the rest is taken care of by what they wrote. So you guys would put whatever you got. Everyone okay so far? Did you find y prime? Does your y prime equal something times c minus x squared to the negative 3/2? That something is what goes into this box right here. Okay? And it should probably be some number times x. All right. It took me a minute to figure out what they meant by RHS and LHS. When I see HS, I think high school, right? So I'm trying to figure out why are they talking about high schools in this problem, right? But what that really means is right-hand solution and left-hand solution. Yeah. So I know they have them backwards. I know. That's on them. So anyway, so your right-hand solution, which is the right side, right, of this equation, is xy cubed over 16. So what they're saying to do is, hey, let's replace this y with what it is. So let's clean up the y and say, hey, if we were to replace the y in here with 4 times c minus x squared to the negative 1/2, we'd get x times 4 times c minus x squared to the negative 1/2 quantity cubed over 16. X, y cubed over 16, right? Okay. All right, so now let's go ahead and cube it. So 4 cubed is 64, so I get 64x over 16 times c minus x squared. What's negative 1/2 to the third? Negative 3 halves, right? So again, I have stuff times c minus x squared to the negative 3 halves. What's 64 divided by 16? 4. Whoa, it's like they match.
Oh, I'm crazy.
Yeah. So they're just having you check, like, is it true? So they have you check the left side by finding y prime, right? And then they have you check the right side by plugging the y in and see if they're the same. Okay. All right. So that's that part of that problem. Now we got to look at the graph. Here's the thing I want you to think about. As x gets close to 0, the slope gets close to 0, and the tangent lines are close to horizontal. As x gets big, the slopes get big, and the tangent lines are close to vertical. So if you have these 4 graphs to choose from, so if I were to label, like yours might be in a different order, but if I call mine A, B, C, and D, which one has slopes that are 0 at 0 and really big at big numbers? D. Okay, does that make sense? Okay. Almost done. Number 1. All right. Do the graphs confirm what you predicted in part A? Well, yeah. Okay, but you got to pick which one of these matches that. So, yeah. For me, it's this second option right here. All right, last thing, find a solution. By the way, this problem is the most mathy of all the problems. The rest go a lot faster. So we're going to we have to find a solution of the initial value problem. An initial value means they've given you the initial value. So we have to go back. I'm going to copy my y and bring it down. So my y, so y equals 4 times c minus x squared to the negative 1/2, right? That's my y. So this y, this is called a general solution. It's called a general solution because it has an unknown constant c that we don't know what it is. That's called a general. If I want a specific solution where I've solved for c, how do I do that? I need a point to plug in. So they gave me, hey, when x is 0, y is 12. So when x is 0, y is 12. So I put a 12 for y, I put a 0 for x, and then solve for c. So you guys have to do the same thing. Plug in your numbers, the number for y, the number for x, solve for c, and then you'll actually get a solution with no unknown constants. that would be mine. Yours is probably different, but that one's mine. I got 1/9 for C. Any questions about the algebra of solving for C? You had to do something kind of like this on your test. Oh, never mind. There's people haven't taken it yet. Just know when you have a root, you have to square both sides. There's Faith. Were you taking the test?
Yeah.
That's what I thought. How did it go? Good.
So you got that equation. Or is this 2 negative 1 and then 1 is less 1. Well, because that's the different. That's the given.
That's y prime, and you want to use y.
Wait, so 1 over. I'm just having algebra.
Sure.
1 over root C.
Uh-huh.
Do we just?
I just
square it?
cross multiplied to move the c over to the other side. Right, multiply both sides by root c, divide both sides by 3,
Oh.
and then square both sides. You can square both sides first, right? If you square both sides first, you get 9 equals 1 over c, so c equals 1 over 9.
What do you have? What is it over? Is it over 4?
Any other questions? Faith, we're doing your homework in class. But we're recording, so if you need to go back and see the first problem, you can watch the recording. All right, I'm erasing. We're moving on.
Did it wrong.
All right, if you got it wrong, I'll help you during core. All right, a population is modeled by this differential equation. This would be a logistic model. So we have 1.2p times 1 minus p over this 4,300 would be the what? Carrying capacity. That's your carrying capacity, right? That's the maximum. The population can't go higher than that. So, for what values of p is the population increasing? Well, a function is increasing when its derivative is positive, yeah, and decreasing when the derivative is negative. So let's make a derivative sine line. So in order to make a derivative sine line, we first need to find the values of p that make the derivative 0. So if I set this equal to 0, I get p equals 0 or p equals 4,300. All right, so there's my two critical values, right? So if I make a sine line, so first question, if this is a population, am I going to have values over here? No, no negative numbers because it's population. As long as there are no zombies. All right, so if I pick a number like 1, this is positive, and then 1 minus 1 over 4,300 would be positive. I get a positive times a positive, I'm positive. If I pick a number like 10,000, I get a positive times a negative, right? So my population is increasing from 0 to 4,300 and decreasing from 4,300 to infinity, essentially. I would write those, they ask for intervals, I would put them as open intervals. So, increasing, I would put 0 to 4,300 as an open.
Yeah.
Or whatever your numbers are.
Yeah, and then for 4,100 to negative infinity for decreasing.
No, 4,300 to positive infinity. Right?
Yeah.
Okay. Because we're talking about an interval, not the actual population. Yes. Okay.
So you can go till infinity even if it's population.
This is a time. These are time, like, oh no, these are p-values. You're right. So, yeah. So as the population goes to infinity, it's decreasing, which would need, all that really means is if your population is higher than the carrying capacity, it's going to continue to decrease all the way down, all the way to infinity. And basically what happens is it kind of levels off at the carrying capacity again. Okay, so I'll write this in. So I have 0 to 4,300. I have 4,300 to infinity. What are the equilibrium solutions? These are the solutions where there is no rate of change of the population. 0 and 4,300. Any questions on number 2? We're okay? All right, number 3. It's a big matching problem. So you have to match the differential equations with their graphs. It's actually not bad. So take a look at letter A. Before we do any matching, let me ask you a question. X squared plus y squared is always going to be what?
Circle.
Okay, I'm not talking about a shape. Okay, if that's x squared plus y squared equals constant, you're right, that's a circle. Okay, let's just say in general, if I plug numbers in for x and y, x squared plus y squared will always be positive, right? Or 0, right? Okay, but it's good that your brain goes to circle because that'll help you next year in Calc 3. So anyway, all right. So here we're saying that y prime equals 1 plus x squared plus y squared. Well, the smallest value x squared plus y squared can ever be is 0, which means the smallest value that y prime can ever be is 1, because you're adding 1 to it, right? So y prime equals 1 plus x squared plus y squared is always going to be greater than or equal to 1. Now, do you want to stop here or do you want to keep going? Okay. All right. So this means since y prime is always greater than or equal to 1, and then if you plug in really big numbers for x, what does y prime approach? Infinity. All right. The only curve satisfying these conditions where the slope is always greater than or equal to 1 and approaches infinity as x approaches infinity is which graph? If for mine it's 3. I don't know if yours are the same or not, but for mine it's 3. Is that okay? Is that okay? Okay. All right, next one. Quick question. E to any power in the whole world is always what? Positive, right? So, y prime equals x times this e is always what if x is bigger than 0? Always greater than 0. Not greater than or equal to, because x is positive. Then this has to be positive. All right. And if x is less than 0, then this is going to be negative or less than 0. The only curve with negative tangent slopes when x is less than 0 and positive tangent slopes when x is greater than 0 is which one? 1. All right, let's look at the next one. Y prime equals 1 over 1 plus e to the x squared plus y squared. All right, this whole thing is always what? Positive. Always positive, because e to any number is positive. However, if x goes to infinity, which means this term goes to infinity, what does y prime go to? 0. The only curve satisfying the conditions where the slope is always positive but approaches 0 as x approaches infinity?
Oh, no,
Two. Or two. Four. Four. Who's the next one?
But the slope of 2 is not positive.
The slope for 2 isn't positive, it's just flat 0, right? So we can't have that. It's got to be 4. Has to be 4. Slope is always positive, but approaches 0 as x approaches infinity. All right, last one. Hey, if y is 0, what is the y prime equal? 0, no matter what. Always 0 at y equals 0. So if we have a y value of 0, which graph will always have a slope of 0 when y is 0? 2. All right, done. Submit. All right.
those green eggs are so sad.
I know. Aren't they nice? I know. I agree. Yep. Okay. Almost done. These look long, but they actually go fairly quick. All right. So this one, I know it looks huge, but it's not that big of a problem. What's nice about these homework questions is each of them touches on something we are going to hit during this next unit. So it's almost like a preview of what's to come. All right. Suppose you have just poured a cup of freshly brewed coffee. Just sounds so nice. Okay. All right. With a temperature of 98 degrees Celsius in a room where the temperature is 20 degrees Celsius. When do you think the coffee cools the most quickly? So do you think the coffee cools the most quickly when you first take it away from the heat source or after it's been sitting in the room for a long time? First take it away. So when you first remove the coffee from the heat source, the temperature starts to drop pretty quick. But as it sits around for a long time, then it's still dropping, but not nearly as quickly. All right, so when it is removed from the heat source. The rate of cooling decreases towards 0. We're talking about the rate, not the temperature, the rate, right? The rate of cooling decreases towards 0 since the coffee approaches room temperature. This is called Newton's law of cooling. Newton's law of cooling says the rate of change of the temperature of an object is proportional to the difference between the temperature and the temperature of the surrounding medium. So how do we write that? So K is, so whenever you say is proportional to, you say equals K times. And it's proportional to the difference between the object's temperature and the room temperature. So what did we call these things? So write a differential equation. Okay, T is an independent variable representing time. Y is the dependent variable representing temperature of the coffee. And R is the temperature of the room. So it would be Y minus R. Time is not involved in this differential equation. It would be in the solution. You'd have temperature at any given time, but the setup is just this, that the rate of change of the temperature is proportional to the difference between the temperature and the temperature of the surrounding medium. All right, what is the initial condition means what's the temperature of the coffee at time 0?
91.
Okay, 91 for you? Sure, okay. Mine's 98, yours can be 90, whatever it is. 95.
Oh my gosh, mine is 95 too.
Oh, okay. All right. In view of your answer to part A, do you think this differential equation is an appropriate model for cooling? Well, yeah, I mean, Isaac Newton wasn't stupid, but let's go ahead and figure out why. Okay, so the answer and the model. Okay. Support each other? Yes. Because as Y approaches R, meaning as the coffee approaches room temperature, then the rate of change approaches what? 0, right? So 0. And then, so the model seems appropriate. Okay, so now what we want is a rough sketch of the initial value prop. So we're sketching the solution, not the rate of change, but the actual solution. So what's the initial value? What's y of 0? 98, or whatever your initial value is. So at time 0, you better look for a graph that starts at whatever your y of 0 is, and then it should flatten out towards room temperature. Yeah, mine is 20. Yes. So mine was this one. I don't know which one yours. Okay. All right. All good? Last one. Okay. So I gotta be honest, I'm dying to just, separate this off, but that's okay. So instead, what we're gonna do, this is what they want you to do for this. They want you to, for each of these y's, they want you to find y prime and then plug in y prime for y prime and y for y and see which one gives you a true equation. So here's what we're going to do. We're going to use our resources. You guys are going to do the first one. All right. You guys are going to do the second one. You guys are going to do the third one. You're going to do the one up here. Don't worry. We'll generalize it. Okay? So first, second, third, fourth, and fifth, middle group.
Sweet.
Okay, the rest of you guys can just sit and watch them work. Yes.
Can you mean like separate,
So what I want you to do, if you're doing the first one, is all I want you to do is find y prime.
Oh, just differentiate.
Find y prime, yep. And then plug in y prime here and y here and see if you get a true answer. Bless you. You're doing the second one.
Differentiate that.
-6x to the what did you grab?
6
X negative. No way.
The second one does not work.
No, because it becomes
32x equals 60x.
Okay, so thank you. So I got a no for the first one.
Second one's no.
Second one is a no.
Last one is a no.
Last one is a no. Okay, so no, no, no.
We got 3 guesses. I say we just.
All right, let me try. Are you guys working on these 2 minute ones?
Check them out.
She just said her equal.
Cool. Again, I'm getting a negative 16x. I'm saying no. All right. Did you guys try this fourth one?
I'm pretty sure it's
You think it's the fifth one? You think some group told me wrong? Really? So the little group from the back was yelling it out and they were wrong? Here, I'm going to try the fifth one.
I just tried the fourth one.
Fourth one doesn't work?
Alright, so it has to be.
So 8 plus 6x to the negative second. So we get x times 8 plus 6 over x squared plus 8x, oops, that's a minus 6 over x. It is. There's your 8x. plus 6 over x plus 8x minus, it is the last one.
Wow.
Or just go really smart.
Okay, so if you are doing this, look for one where this first number, I'm guessing, is going to be half of this number there, and then yours minus something to the negative first. Okay.
Oh.
All right, are we good?
Yep.
Yay! All right, let me reduce this.
Now we'll have to do another break.
All right, so that means, so I turn off this recording.